In this video, and as a matter of fact, for the entire week, we're going to be talking about confidence intervals, which is chapter 8. Right? So all of the videos for this week will talk about or discuss what are called confidence intervals. So there's a lot to unpack here, and it'll take us the whole week to get through chapter 8 and may even spill over into next week. So the first thing that we're going to talk about is something called the statistical inference life cycle, because we've actually moved into a sort of the third part or the third unit of our book. So 1 through 4 was one kind of thing, and then 5 through 7 was another kind of thing, and now we're getting to the third unit of our book, which is statistical inference. And as such, I need to talk about a little bit the important ideas behind statistical inference. And so that's what I'll do first. Then we'll talk about something called point and interval estimates. And then we'll talk about a confidence interval for the population proportion. And lastly, a confidence interval for the population mean. Okay, of course, all of these will be split up into different videos. So first I want to talk about the statistical inference life cycle, and I'm going to change of which I've already done. And in fact, if you were in class on last Wednesday, we've already talked about this. We start off in every statistical sort of question that we're going to ask and task that you're going to do with a population in mind. Okay, so you're interested in a population, which I have as a box here, okay? And specifically, you're interested in a certain aspect of that population. So my usual example is my population is Shippensburg University, and I'm interested in the mean GPA of all Shippensburg students, okay? Of course, that question can be answered by going to the registrar, but suppose that the registrar doesn't like me, and so they're not going to give me the answer. So what I can do, I have that population and some unknown, what's called population parameter. So I believe we defined that a little bit before, maybe in chapter 6 or 7. We have a population parameter. It's a fixed value that I don't know, but I'd like to estimate, or I'd like to say something about. So I'm a long way off from that at the moment because I don't know what it is, and all I have is a population in mind. What I can do, and what we focused on in chapter 7, is that I can take a sample from that population. And so we've talked about taking a sample lots before. In chapter 4, we talked about good and bad ways to sample someone and so forth. From now on, we'll always assume that we're sampling using simple random sampling. So we know everyone in the population, and each person has a 1 over the number of people in the population percent chance of getting picked. Okay, so just completely random. At random, people are picked. Okay, and so suppose I sample 10 people from the Shippensburg population. Okay, so I take a sample of size 10 and then I write that, and so we'll look at like sample 1. Okay, I take a sample of size 10. I look at it. Okay, that's what we sort of did in the first couple of chapters. We looked at this data, and then if I'm interested in ultimately saying something about the population mean, okay, the logical thing for me to do is to calculate the sample mean of that sample. Okay, and so I do that. So I take a sample, and then I calculate a statistic from that sample. Okay, X bar 1. But of course, I could do this, and to get a really good idea of the population mean, I should do this more than once. I should do this many times. Okay, so theoretically, I can do this many times. I take not just one sample, but many samples from the population. So you'll see I have them labeled 1 through n. Okay, I take many samples from that population, which I can turn into many statistics. So I no longer have just one statistic, x bar 1, I have x bar 1 through x bar n. When I combine all of those statistics in a graphical display of how they fall, I get what we call a sampling distribution. So we talked about in chapter 7 sampling distributions. That's extremely important. Okay, and we sort of solve this statistical inference life cycle in the special simulation that I showed. Instead of going left to right like I do, they went from top to bottom. So theirs was like a vertical picture of this. Mine's horizontal. But anyway, we take many samples, which turn into many statistics, and then we find how the distribution of those statistics look, and that's the sampling distribution. And then the last thing that we do, which is what we're going to do in this chapter, is, and it's the hardest one, is to go from that sampling distribution and then try to say something about that population parameter I'm ultimately interested in. Okay? So that's what we're going to try to do, is that last step that we have in red, trying to go from our sampling distribution back to the population. And of course, in practice, it's often not feasible to take many samples. We often take one sample, okay, and we calculate one statistic. But we rely on the theory behind this, behind something like a sampling distribution, to say this is how, if I took many samples, this is how it should behave. Okay, so that's not perfect, but it's sort of what we have. And it's we can theoretically back it up. We won't talk about any of that in class, in this class. If you take a more advanced stats course, something like Math Stat, okay, really later on in your undergrad career, then they would talk about sort of why this is okay theoretically. You'll just have to trust me here. So that's the statistical inference life cycle, and we're trying to take the information that we have, the one sample that we have, and the theoretical sampling distribution about the statistic that we created to say something about a population parameter. Okay, and so it's here. The first section that we're going to talk about is a point and interval estimates section. Okay. So a point estimate is a single number that is the best guess for the population parameter. So we have this unknown population parameter, and if I forced you to say one number that you think would be sort of the best guess at estimating the population parameter, that would be a point estimate. Okay, so if I said I'm interested in the mean GPA of all Shippensburg students, and I said you have to give me one number that's your best guess. Here's the sample that I took. Then whatever statistic that you create that you think is the best guess for the population, that's going to be your point estimate. Okay, it's a single point, and so it's called a point estimate. However, an interval estimate is an interval of numbers that is believed to contain the actual value of the parameter. Okay, so that's an interval. So instead of giving me one number, you are going to give me a range of numbers. Okay, so for instance, for a point estimate, you would say, well, I think that the best guess for the mean GPA of Shippensburg is 2.9, okay, or 3.0. Whereas in an interval estimate, you'd say, well, I think that the GPAs are going to be the mean GPA is probably going to be around 2.8 to 3.1. Okay, so you're giving me a range of possible numbers. So here's a visual estimate, okay, a visual picture of these two estimates. A point estimate is a single number. An interval estimate is an interval number. Now, most likely, an interval, and especially in our cases, are going to be formed using a point estimate as the sort of starting point. But it stretches out what we previously thought was our best guess to a range of possible numbers. So a point estimate is not enough, okay, because there's too much uncertainty about sample to sample variation for us to be confident in that one point estimate. So again, you're interested in the population parameter, you take a sample of size whatever, and then you calculate that statistic that you want. That's going to be your point estimate. But you're probably not happy with that, or you shouldn't be, because you have to trust that that sample is representative of the population. If it's not, then your point estimate's going to be way off. And that's not a good thing. So even though they're not enough, we can start an interval estimate with a good point estimate, and so it's important to talk about what makes a good or bad point estimator. Okay, so I'll make a distinction here between estimate and estimator. An estimate is the actual number that we get. An estimator is sort of the process that we get it, so the idea behind it. So what makes a good point estimator? The first thing that we want to talk about when discussing a good point estimator is unbiasedness. Okay, so to be unbiased, or a point estimator is unbiased, if the mean of the sampling distribution of the point estimate is equal to the population parameter. Okay, so as an example, if my point estimator is x bar, the sample mean, and my population parameter is mu, if you'll remember, the sampling distribution of x bar is approximately normally distributed with a mean of mu and a standard deviation of sigma over the square root of n. So it turns out that x bar, the sample mean, is unbiased. Okay, so it's unbiased because the mean of the sampling distribution is equal to the population parameter. Okay, so it's unbiased when estimating mu. If it were trying to estimate something else, like sigma, then it wouldn't be unbiased. But it is for mu because mu is the mean. Something like another thing that we could choose to estimate the population mean could be the sample median. Okay, so x tilde is what I'd call the sample median, but the sample median may not be unbiased. Okay, it may have a mean of something else. Okay, but the sample mean is unbiased with respect to mu, and so that's a good thing. And the other statistic that we'll talk about a lot is p hat, and it's unbiased for p, the population parameter. Okay, so that's one part of a good point estimator. The other part is something called minimum variance. Okay, and so we want an estimator to be unbiased, and we want it to have minimum variance. And minimum variance means that the estimator has a smaller variance or standard deviation. Okay, we talk about standard deviations, but other people tend to talk about variances. It has a smaller standard deviation than other estimators. Okay, and so for instance, if I have two histograms here. Okay, one is X and one is Y, so you can see that on the top. Estimator X, they both have a center or have a mean of 50. Okay, so they're both, we'll say, The true value is 50. Okay, they're both centered on the true value, but you'll see that estimator, so they're both unbiased, but estimator X over here, its estimates are much closer to the mean than Y, okay? Or you'd say that estimator X has a much smaller variance than estimator Y. They're both unbiased, but they have estimator X has much smaller variance. And that's preferable because you only take one sample in reality. Okay? You only take one sample. And so you want to take that sample and have an estimator that has a small variance, because then you know that should be close to the true value. Whereas with Y, it's very possible that you have an estimator that somehow has a mean of, your estimate is out near 75 or 25. Okay, whereas in estimator X, your estimates are most likely going to be at most 55, at least 45. Okay, so hopefully that made sense. An interval estimate is better because it indicates more precision. Okay, we get a more precise answer by giving an interval of numbers around the point estimate. So maybe I shouldn't say precise there, but it's going to give us a better chance of encapsulating the truth than just a point. Because if the point is just a little bit off, then of course it doesn't contain the truth. Okay, but we could give an interval of numbers, and that is much more likely to contain the truth. So in this course, we're going to focus on what are called confidence intervals, but there are other interval types. And so the most popular other one is called a prediction interval. And so if you take Stats 2, you'd talk about prediction intervals. Okay? A confidence interval is made up of two parts. You start with a point estimate, and then you add the margin of error. Okay? So the margin of error is an extremely important concept. It's a measure of how accurate the point estimate will be at estimating the parameter. Okay? It's made up of two things: the standard deviation of the point estimate and some level of confidence. And we'll talk about both of these things later. The standard deviation of the point estimate is you have to look at the sampling distribution, and then that's where you get that standard deviation. Okay, so our general form of an interval estimate or a confidence interval is always going to be the point estimate plus or minus the margin of error. Okay, and so if you had to explain the margin of error to a lay person, okay, or anyone else, my guess would be, okay, that you would. So actually, if you were trying to explain the margin of error to someone who was working at a fast food restaurant, okay, not that they aren't smart and they can't understand anything, but I'm just trying to give a context where I could explain the margin of error. So the margin of error would be, you could think if you ordered a large fry, okay, a large French fry from some fast food restaurant, okay, you're going to get, every time, you're not going to get the same number of French fries. Yeah, sometimes there'll be a little bit more, sometimes there'll be a little bit less. Okay, there should be an average number of fries that are there, and that's sort of the number of fries that you'll get from a large fry. That margin of error is sort of the difference in the number of fries that you get from time to time. Okay, roughly it's like that. Okay, so we're almost done here. What is a confidence interval? What does the confidence in a confidence interval mean? Okay, so it's an interval and it's talking about confidence. What does that mean exactly? Okay, so as an example, here we don't really know how to form this, but a 95% confidence interval for the proportion of students who are excited about switching to online classes could be 0.18 to 0.22. So I'll say that I made this example last spring, and so right when we had switched online. But I'm guessing this would be about the same if we switched online this semester. Probably not very many, but 95% confidence interval for the proportion of students who are excited about switching to online classes could be 0.18 to 0.22. Okay, so that's my confidence interval. When we talk about confidence, we really need to talk about the interpretation of a confidence interval. Okay, and so we haven't really talked about how to form it, but hopefully you have an idea of what it is from our past couple of slides. We start with our best guess, okay, and then we add and subtract some margin of error. And our ultimate goal is to encapsulate the true proportion, okay, of students who are excited about switching to online classes. We don't know exactly what it is, but we're trying to encapsulate that in this range of numbers. Okay, the first and usual interpretation that students and really anyone comes up with is that there's a 95% chance that the true proportion is between those two numbers. Okay, so I think there's a 95% chance that the true proportion of people who are excited about switching to online classes is between 0.18 to 0.22. But in fact, that is wrong. Okay, so you made this interval, and the truth is either in it or it's not in it, right? So there's not like a 95% chance that it's in there. The truth is out there, and so it's either in it or not in it. So that is in fact not the interpretation of a confidence interval. Here it is. It's going to seem weird, and we'll come back later and discuss this again, but it's important to introduce so that we know what confidence means. So the correct interpretation is if we construct not just one interval, but many intervals using that same method. So what that means is I take not just one sample, but many samples. Okay? Using that same method, then 95% of those intervals should contain the true value of the parameter. Okay? So what that means is if I take many samples, okay, and then I use my mean plus or minus margin of error approach, okay, to a confidence interval, if I use that on every sample, then 95% of those intervals should contain the true value of the parameter. Okay, for every interval, it's either going to or not going to. There's no like 95% chance that it does. It either is or it isn't. The 95% comes in is if we construct many of the intervals, then 95% of those intervals should contain the true value. Okay, so in essence, our confidence is in the method that we used, not the actual interval of numbers. Okay, so the confidence is that if we used a good method, a method that's going to construct intervals that 95% of the time will contain the true value, not the actual interval itself. Okay, and so there's a quick simulation here that I want you to watch from a nice book, and you can do this yourself, but we want to do a confidence interval here. And so we'll select a normal population, okay, and we'll choose a sample of size 10, and we want to create a 95% confidence interval, okay, and it's going to start sampling, and it's going to calculate how much percent of the intervals contain mu. Okay, and so we should see that 95% of them contain mu and 5% exclude mu. So if we start to sample here, you can see that it'll sample and then create an interval every time. Each interval is not going to be the same length, okay, and it's certainly not going to be the same spot. But you'll see here that many of the intervals contain the truth, okay, and they have the truth. There's a black dotted line, okay. Many contain the truth, but some do not. And it turns out that hopefully 95% contain it and 5% don't, because that was the method that we used. Okay, so over here, if we do this, if you hover over the thing, you'll see that right now 95% do and 5% don't. Okay, and as you continue on, the percentage will change slightly. Okay, now we're 96 and 4, but you see that around 95% of them do. But for every interval, every line here, it either contains it or it doesn't. So the confidence is in the method that we use to create these intervals, not the actual intervals themselves. Okay. So that's it for this video. We'll come back next time and actually do some stuff that you can do your turns on.